Can you see my screen? So today is 4th. So is everybody comfortable with quotient topology? So it is your time. Those who are not comfortable can say, right? I will not ask again. So does that mean everybody is comfortable? All right, fine. So what do you mean by quotient? You have seen the quotient construction everywhere, almost every subject. So what do you mean by quotient? Taking quotient? Hmm? What do you mean by doing? I mean, taking this quotient. It's kind of identification. It's kind of identification. So little bit of quotient topology. So for example, if you have this kind of strip and you, let's say you add this with identify this and this, right? So what is it? You have piece of paper like this. You have piece of paper like this, and you identified it like this. So you identified. So what do you get? Cylinder, right? So it's something like that. So that means this point, let's say this, look at, write it properly. So this is x-axis, this is y-axis, this is 0, and this is 1 comma 0, this is 0 comma 1. So you identify x comma 0 identified with x comma 1, right? So you say that x comma 0 is equal to x comma 1 after identification. These two are related. And then you are quotienting out. So then what you get, you ultimately get is a sphere. right? Now look at this sphere in x-axis. So look at this sphere also. This is another construction. Suppose this is oh well, I would look at this sphere in the following way. I would look at the ascending form, right? Now you suppose this point is this is yz plane, xy plane, and this is z axis. So this is suppose this is the coordinate, and this is z axis, x axis, y axis. So and this is plane z equal to 1, this plane. So suppose you identify this one, this circle with this circle, right? Identified this. So that means x comma y comma 0 identified with on the circle on the cylinder x comma y comma 1, right? You identify this. So after this identification, what do you get? Anybody? What do you get?
Torus.
Right. It's a torus. So of course, let me write it in this form. But of course, it will be upside down torus, right? So you get a torus. So torus, which means these are circles in the torus. These are circles, the torus. The circle. So we have that cylinder, and then yeah, in paper it's different. So we have cylinder and then identified with torus. But you see here, this cylinder, open cylinder. So if you remove the circles, end circles, this is a manifold. And if you keep the boundary circles, for example, a tube, it has ends also. This is not a manifold. But your tube is added to the ends, something like this, you get torus. Torus is a manifold, right? So here, this is just an exercise, simple exercise. Show that the torus is a manifold. So the way you get torus, and this is isomorphic or diffeomorphic to S1 cross S1, right? But you do it from this construction that this is manifold. All right. Okay, so few things about quotient topology. So suppose you have a set S, right? And you gave an equivalence relation, right? You give an equivalence relation. Now, once a relation equivalent, you can look at equivalence classes, and you can look at class of, I mean, the collection of all equivalence classes. That is actually gives you a quotient. So suppose what's going on? suppose S is a set and this is an equivalence relation. On S, right? Then this S quotiented with this relation, this will be this is the notation for the collection of all equivalence classes. All right. Now you want to give a topology, right? So now how to give a topology? Can anybody answer this question? How to give a topology on this? You have seen what is quotient space is. Quotient topological space you have seen. So what is give a topology on this?
So first we'll define like a map from S to this equivalent classes,
Mm-hmm.
and then we will say a subset of this this quotient space is
Mm-hmm.
open if
Mm-hmm.
the inverse map with that inclusion is open.
Right. Exactly. So you first define a map. So define a map is called quotient map. So S to S quotiented this pi. So by X is the equivalence class of X. Right? Simple now. X goes to equivalence class of X. Now the idea to get a topology on this is the following. Now, a topology which will make the quotient map pi continuous. All right. So, what is the definition of continuity in a topological space?
Inverse image of open set.
Of course, yeah. Right. So that's how you get the definition. Now, in a topological space, now in a topological space, a map F is continuous. So a map let me write it in a better way. A map F from X to Y, XY topological spaces is continuous if or is said to be continuous if F inverse U is open for every open set U in Y in X, right? So this is the definition of continuity you all know, so you'll use that one. So in case of quotient topology, in case of quotient, we define a set U in S is so open in if phi inverse U is open in S. Right? So S is already a topological space that is given to you. So now, I mean, the quotient space, you need to give a topology. So we'll look at those sets for which the inverse image is open. All right? Now this gives a topology. This gives a topology on this, which is called the quotient topology. Right? Now, is the quotient topology house drop? Is the quotient topology house drop? Yeah, anybody? Is the quotient topology house drop? What happened? Do you think it will be house drop? Hmm?
May not be.
Yeah, do you have an example? Yeah, it is true that it need not be house drop all the time. So, yeah, do you have an example?
Sir, I can think one like I can recall one like we had two lines,
Yes.
and then in the two lines, the first points were not identified. They were like as is, and every other point other than the leftmost point was identified between the points. As in 0, comma x is identified with 1, comma x.
Okay. Yeah, yeah, you are right. So the point is, it's very standard example. So look at this line. Look at this line. So this is, let's say, x-axis. This is y-axis. And this is y equal to 1 line. Right? So your set is these two lines. Y equal to 0 and y equal to 1. So you identify x comma 0 with x comma 1 for all x not equal to 0. Is it an equivalence relation?
Yes, sir, we can check.
Right. So this is an equivalence relation. And you see, this is called line with true origin. Now, these points will be separated, and these 2 points will be there. All right. All other points are identified.
So this will have the similar topology as that manifold we were talking about in the first problem.
Right. Exactly. Exactly. So the topology will be exactly same as we have seen in the first problem. Right. So open sets will be like this. So if it is outside like this, or it would be using this points, or and this replaced by other points, right? It's like IA of minus c comma d and IB. So A is here and B is A is this point and B is this point. So IA of minus d comma minus c comma d and IB of minus c comma d, something like that, right? And this is we already know this is not Hausdorff. This space, so A is concentrated with this. S is union of two lines. So S is x comma 0, x is in R, union x comma 1, x is in R. So this is not a Hausdorff space. All right. So Hausdorff is a problem. So if it's not Hausdorff, then you can say this is a manifold, right? All right. So another example. In that case, it will be manifold. Closed interval 0, 1. Is it a manifold? Is it a manifold, a closed interval? Come on, answer this. This is very simple, right?
No, sir, at the point 0, it won't have a locally Euclidean.
Right, 0 and 1 will have problem. Right? You will not get an interval in open interval in real line, which is homeomorphic to an open subset around 0 and around 1. Right? So this is not a manifold. But it's a manifold with boundary. It's not a manifold. Because it's not locally Euclidean around 0 and 1. But you give a map, cosine map Q. Let's say Qx equal to e to the power 2 pi Ix. Right? Now what is the image of this?
This one.
H1, right, circle. Unit circle. Right? So now this is a manifold. So sometimes by cosenting you might get a manifold. In general, in the beginning, which may not be. So this is a cosine map, right? This is just the endpoint identification. 0 and 1 get identified to a single point. Now it becomes a manifold. All right. Any question here? Any question? So one other thing, one other few important things. This is the following. So you have suppose uh, S2, S is a set, and S quotient topological space, and S quotiented with this equivalence relation. Suppose you have a map from some topological space F from S to Y, let's say. Then what you can do have is as follows, right? So then you can have one map, right? Say till, right? So if F is this much, then define. These are very natural construction. So you should remember that. You already have seen it. Class of X is nothing but Fx. Or if F of, right, for all X in S. This is the definition. So the inverse image of a single point, it might be whole set or it might be anything, right? So then all these things gets identified here under F tilde. Right, another example. These are few construction will be important later on. So suppose you have R2.
We need a restriction on that F, right?
What?
F should take all the points of an equivalence class to one single point.
Ah, that is true. That is true. That is true. So, so in general, it might not be. Yeah, for any map F, you might not get uh, F tilde, right? So what you need is the following. So F should satisfy F, yeah, satisfy the following: F of X equal to F of Y if X is related to Y. That is important to define a map from the quotient space, right? This is important. This is required. All right. Yeah. Thanks. Now you consider this as an example. So yeah, another point is this. Once you define this diagram, once it is defined, once F tilde is defined, then the following is true. F is continuous. You cannot leave. F tilde is continuous. Okay, so this is, try to prove it. I'm not going to prove here, but this is a fact. A very simple fact. By using definition, you will get it. Yeah, now what we are looking at is the following. Right, so this is x-axis, and these are all lines parallel to y-axis. So you look at R2 as this one. So and define a relation x y is identified to p comma q if y equal to q. Is it an equivalence relation? So xy is identified with p comma q if, so these are all points in R2 if y is equal to q. The last coordinate is the same. So what do you mean by last coordinate being the same? That means it lies in one of the lines parallel to y-axis. Right? All the points here gets identified. Right? All the points here gets identified. All the points here gets identified. So is it an equivalence relation?
Yes, sir.
All right. So this is an equivalence relation. This is an equivalence relation. All right. Now, if you quotient R2 with that, what do you get? Any guess?
R.
Right. It should be isomorphic to R. Is homeomorphic to R. Right? So you have natural projection map, sorry. You have natural projection map R2 to R, xy goes to x, right? Natural projection map. And this is not just a quotient map. This is very important. This will form a bundle, which will generally not cover it, uh, but this is a nice kind of stuff. So the following theorem is an exercise. Those who are not comfortable with quotient topology. So when the quotient space is Hausdorff, right? Can you tell me when the quotient space is Hausdorff? Mm-hmm. So suppose S is a topological space and define R as x comma y in S cross S such that x is related to y. All right, this is a relation, equivalence relation. So show that S cosented with this equivalence relation is a Hausdorff topological space if and only if R is a closed subset of S cross S. Right? So this is R is called graph of the relation. Any question? You have seen that a topological space is Hausdorff if and only if it's diagonal in S cross S is closed. That comes from corollary of this one as well. These are basic quotient topology. I mean, if you are interested looking at some proof in some book, then you can open those books. These are there. So another example of a cosine space. So another example. Suppose you have a sphere. Right? You have a sphere. So a point here x comma y comma z. Let's identify it to some points here, which is minus x, minus y, minus z. Right? So x comma y comma z is identified with minus x, minus y, minus z. Is it fine? Is it equivalence relation? Is this an equivalence relation?
Yes.
So yes, the answer is yes. Right. This is a nice space. So I mean, yeah. So is it Hausdorff? Question again. Is it Hausdorff? Well, is it what? Is it S2 cosented with this? Two is S2 by this. Second countable. Space. Yeah. Third thing, of course, is S2 by this. The local Euclidean. What are your guesses? Yeah.
So it is Hausdorff.
Yes?
It is Hausdorff.
It is Hausdorff. Okay. Do you have a reason or just a guess?
Because I mean the open sets. I mean, if I take an open set, so this is technically the it looks like the upper sphere, upper
True.
part of the thing.
Right.
So we can take an open set there, and the inverse will be just that and the opposite, same open set, like mirrored. I mean, just on the opposite side of this too. And we can like take, I mean, make it horse to consider two open. I mean,
I mean, you have to take 2 points and you have to show there exist two neighborhoods,
yes.
which intersection is empty. Right? You will not have problems except the points at the greatest circle on the plane. Right? There some identification is going on. You need to check that. So 2 points. I mean, a point in the lower hemisphere is always identified with the points in upper hemisphere. So it is enough to consider the upper hemisphere union the circle in the plane, xy plane, right? Now, if it lies in the upper hemisphere, not in the circle, Then you can look at the, usual topology, induced topology from R3 and look at small neighborhoods, those which are disjoint. That would give. Now, if some point lies in the circle, then what happens? That's what you need to show. Yeah. Second countable is rather easier because the topology in S2 is coming from R2, induced topology R3, induced topology in R3. Yeah, so think of this question. So next time we'll answer these three, and we'll actually generalize to Sn as well, and we'll look at that in a different point of view as well. Okay. Any question here? Okay then. So we'll meet next time.